Computer architecture, floating point. Let's focus now on multiplications and especially on divisions, because they are quite complicated, as you will see. But first, a very small overview of what we did last time. We had in normal architecture, in any architecture that uses IEEE 754, how the floating point numbers are stored in memory. So let's focus just on single. It has 1 bit for the sign, so it's sign magnitude. Then it has 23 bits for the fraction, to store the information about the fraction, and 8 bit to store the exponent in the number. So for instance, for a single, the number that you get is 1 point, the fraction. So this 1 point is implicit in this bit pattern that is here. It is not written in this bit pattern, but it is omitted because it's implicit. 1 point, the fraction, times 2 to the power x, that is the bit pattern here, this 8 bits stored here, which is then excess 127. So we have to subtract 127 to get the exponent that is then used in the final, in the calculations. We have done some example, I will not repeat that here, but now the idea is that if we multiply two numbers, f1 and f2, we have to multiply the multiply the significance and sum the exponents. And as you can see, that the s1, which we call the significant, is 1 plus the fraction 1, and the significant is 1 plus the fraction of number 2, so that significant 1 times significant 2 is 1 plus fraction 1, or is an error here, plus fraction 2 plus the product of the fractions. And this is a number between 1 and 4, meaning 3 point, etc, etc, etc. Well, I'm not going to talk more about these multiplications because that should be rather obvious by now how that should be done. But because we have also done this with integer number, remember. The problem now is that we also have to do divisions, and divisions are a little bit more complicated. And anyway, we have, since long we have coprocessors, which I will also talk to you about in the MIPS assembly language lecture, which will follow this one. But I want to explain to you how divisions are being done. So this one I can close. A division, A divided by B, is not done directly because it cannot do divisions. Computer cannot do divisions. Strange, it cannot do divisions. It can only do multiplications. At least this one in float. So A divided by B, what it is doing, it is multiplying it by the reciprocal in the numerator and the denominator. This is allowed. And then what you get, that B times the reciprocal of B, that is 1 divided by B, is then actually A times the reciprocal of B. So what we have to do is, if we want to divide A by B, we have to multiply by the reciprocal of B. Well, I will now remove from the reasoning this A, because it will just be a multiplication at the end, and this we already learned to do up there above. So what we're going to do now is to calculate 1 divided by B, which is the reciprocal of B. If we look here, that means that A is 1. So 1 divided by B is the reciprocal of B divided by B times the reciprocal of B. Now let's call this the denominator, what we have here, and here we have the reciprocal of B. The denominator, the idea is to make the denominator 1, because if this denominator is 1, then we have the reciprocal. I don't know if you see this, where this is going to, but if we can calculate, if we can approximate this, make this one 1, then we have here the reciprocal. So that's what we're going to do. We calculate the denominator, we're going to try to make it 1. The denominator is B times the reciprocal of B. Now imagine that we are at a certain moment, we have a certain error, which we don't know yet, but it has a certain error, so it is 1 plus this error. What we do now to find the new denominator is multiply the old denominator by 2 minus the old denominator. So we do some kind of iteration, and if you look at this, follow this, 1 plus E multiplied by 2 minus 1 plus epsilon, sorry, not E, epsilon. This is then 1 minus epsilon squared. And that means that if we had a denominator that was, for instance, had 5 digits precision close to 1, then now it has 10 digits precision close to 1. So when we're doing this, then we're getting closer to 1 in the denominator. And now let me then divide this equation, this part here, by b. So I divide this side by b and this side by b. Don't forget that the denominator was b times the reciprocal, so if I divide now by b, I get the new reciprocal equals the old reciprocal times 2 minus d. You get it? Reciprocal, the new reciprocal of b is the old reciprocal of b times 2 minus this denominator that we found. Let's see where this goes to. So let's imagine we want to compute 1 divided by b, which is 1.0 divided by 3.5. And the initial guess, actually, what we're doing normally, we have a lookup table for that. A simple, very simple approximation, let's say 5 bits accurate. So if we do 5 bits accurate, we have, 32 entries in our lookup table. So the first thing comes directly, it's copied from a table. And we will see 3.5, then the lookup table is 0.3. So that means that the denominator is 3.5. This is our b that we want to calculate, remember? And then the reciprocal of b comes from this lookup table, that's 0.3. And we have now a denominator that is 1.15. Oh, that's quite nice. That is already 15% accurate. But let's now do an iteration. So, as we did here, the new reciprocal of b is the old reciprocal of b times 2 minus d. d is 1.15. The old reciprocal was 0.3, so we do 0.3 times 2 minus 1.15, and that is 0.285. We do another iteration, so we get 0.285, etc., etc. Repeat, we get 0.2857142857, and that in 3 iterations. That is not so bad. But as you can see, that divisions, they take actually iterations that involve multiplications, as you see here, and actually subtractions. Well, subtractions are quite fast, but this multiplication here, that takes a lot of time, and you have to do probably 3 of them. So divisions are much slower than multiplications, and that is why when you write a program in higher level programs, languages, you should try to avoid divisions as much as you can. Imagine you write C++ or you write Pascal. Don't write a equals b divided by 5, but write a equals b multiplied by 0.2, because this is much faster than this. Or if you write something like a equals b divided by c divided by d, much better is to write a equals b divided by c times d, because it will simply be faster, because multiplication is faster than division. So when you can avoid division, do it and substitute them by multiplications wherever you can. Okay, next lecture.